Ladies and gentlemen, welcome to my course about IP addressing. This course offers a lot of knowledge to beginners, but we'll also cover some more challenging topics later on. Let's go through the curriculum so you can see if this course is right for you. The first section covers the fundamentals. In the first lesson, we have a general introduction to IP addresses. The second one will cover different ways to represent an IPv4 address, and in the third lecture we will learn how to convert numbers from binary to decimal format, because this is a skill needed to switch between IPv4 notations. In the second section, we will talk about classful addressing and how IP address blocks are distributed. We will also introduce a new concept called network and host portions of an IP address. The third section will be about classless addressing, and you will also learn how to convert numbers from decimal to binary numeral system. This is because in this section we will be doing some network calculations, and this is a useful skill to have here. Those networking calculations include finding the maximum number of hosts, finding the address of the first and the last host in that network, finding the network IP, and calculating the broadcast IP. The last section explains modern networks. That includes IPv6 addresses, what happens when you try to access a website, the difference between private and public IP addresses, after which you will learn how to set up and configure your own private network, and finally we will conclude the course with a lesson about domain name systems, static and dynamic IP addresses. Good day, ladies and gentlemen, my name is Salman and today I will teach you about IP addressing. IP addressing is one of the most important things in networking and data communications. If you wonder why it is so important, think of it like this. When you are sending a letter, you put it in an envelope, write the receiver's address, write your own address, and then send it off. When the mailman gets it, he looks for the destination address and brings it to the receiver. The receiver looks at your address, so he knows who is sending the message, and then probably proceeds by reading the letter. A network communication works in a similar fashion. Instead of the letter, you are sending data in forms of zeros and ones. The source and destination IP addresses are written in the header of the data packet. Finally, instead of the mailman, we have the network layer, which is responsible for the delivery of data packets. In conclusion, IP addresses are very important because without them, data communications would be impossible. Without the destination IP address, the network layer wouldn't know where to deliver the data packet, and without the source IP address, the receiver wouldn't know who sent the data packet, and therefore couldn't respond to it. Communication at the network layer is called host-to-host communication. A host is basically a computer. So we have a computer somewhere in the world that needs to communicate with another computer somewhere else in the world. Usually this communication occurs through the internet. The data packets may pass through several other networks before they reach the destination. For this level of communication, we need a global addressing scheme. This scheme was called logical addressing, but today this term is replaced by IP addressing. The internet addresses are 32 bits in length, which gives us a maximum of 2 to the power of 32 addresses. These addresses are referred to as IPv4. For today's standards, this address range is very limited, because we have a lot of networking devices. The numbers of networking devices are increasing every day, making the range of available IPv4 addresses even lower. The need for more IP addresses motivated the development of a new technology called IPv6, which is 128 bits in length. It's only a question of time before IPv6 becomes more dominant, but let's focus on IPv4 for now. IPv4 addresses are unique and can represent one and only one connection to the internet. Two devices on the internet cannot have the same address at the same time. Note that I said at the same time. This means that an address is assigned to a device only for a certain time period. When this time expires, the address is taken away and reassigned to another device. There are some devices that require more connections to the internet, and therefore they have multiple addresses to operate. A good example of such device is a router, which operates at the network layer. There are two main notations to represent an IPv4 address: binary notation and dotted decimal notation. Let's talk about binary notation first. As I mentioned before, an IPv4 address consists of 32 bits. A bit can have a value of either a 0 or a 1. This means that an IP address in binary notation should look something like this. We have 4 groups of 8 bits, and as we all know, 8 bits grouped together represent 1 byte, so we can say that an IPv4 address is made up of 4 bytes. When it comes to the dotted decimal notation, we will use the same example. We just need to convert those bytes from the binary to decimal numeral system and separate them with dots. This form of address might seem more familiar to you because it's more widely used in this format for the purpose of easy reading. Please note that in this notation the highest possible number is 255, because that's the highest number we can write using 8 bits. Let me demonstrate this for you. We have place to write 8 zeros or ones. Naturally, a 1 represents a higher value than a 0, so if we want to write the highest possible number, we will fill all the places with ones. When we convert this number from binary to decimal format, we will get the number 255. In the next lesson, I will teach you how to convert numbers from binary to decimal format. There's 2 ways of doing it, and I will teach you the hard way, and the easy way is pretty much self-explanatory. Hello again, ladies and gentlemen, and welcome back to my course about IP addressing. As promised, in this lesson I am going to teach you how to convert numbers from binary to decimal format. If you're not really interested in learning this conversion or you think it's useless, I will just show you the quick and easy way to do so, and you can skip off the rest of the video. First, you need to open up a web browser, whichever you prefer. I will use Google Chrome in this example. We need to search Google for binary to decimal converter and open up any of these links that come up. Let's just go with the first one. We need to write in a binary number, for example 11001001, and click on convert, and the site will give us the number in decimal form. If you want to know how to convert numbers from binary to decimal without using any tools, Google and so on, I will show you an easy method to do it yourself. Let's use the same example as we did before. It was 11001001. We need to convert this number to the decimal format. The first step to do is to write little exponents above each of these numbers, starting from right to left and starting from 0. So we have a 0 here, 1, 2, 3, 4, 5, 6, 7. If we see a 1 here, we write 1 times 2 to the power of whatever exponent here is. So we write 1 times 2 to the power of 7. Plus, we have another 1, that means 1 times 2 to the power of 6. Plus, if we see a 0, we don't write anything. Again a 0, and then again a 1, so we write 1 times 2 to the power of 3. Plus, a 0 again, we don't write anything, 0 again, and another 1, so we write 1 times 2 to the power of 0. If we multiply this by 1, it's going to return the same value, so we can just write 2 to the power of 7, plus 2 to the power of 6, plus 2 to the power of 3, plus 2 to the power of 0. 2 to the power of 7 equals 128, 2 to the power of 6 equals 64, 2 to the power of 3 equals 8, and 2 to the power of 0 equals 1. When we sum this together, it's going to return 201. Keep in mind that anything to the power of 0 equals a 1. So for example, if we have 99 to the power of 0, it's going to return a 1. And if we're going to do 5 to the power of 0, it's still going to be a 1. A common mistake that people do is they write these exponents starting from 1. If you want to have a correct result, we need to start from 0. I will show you a couple of more examples using binary numbers that have a different length. So let's say we have a binary number that has only 4 bits, for example 1, 0, 1, 1. Now this fact doesn't change anything in the method, so the first thing that we need to do is still write the little exponent starting from 0. 0, 1, 2, 3. We see a 1, we write 1 times 2 to the power of 3. Plus, if we see a 0, we ignore it. We see a 1, we write 1 times 2 to the power of 1. And we have another 1, that means 1 times 2 to the power of 0. So we have 2 to the power of 3 plus 2 to the power of 1 plus 2 to the power of 0. 2 to the power of 3 equals to 8. 2 to the power of 1 equals to 2, and 2 to the power of 0 equals to 1. So the result is 11. Let's try another example, but this time using a huge 11-bit number. The fact that it's long here doesn't change anything in the method. Still, the first thing that we need to do is write the little exponent, starting from 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we see a 1, we write 1 times 2 to the power of 10. Plus another 1, 1 times 2 to the power of 9. Plus another 1, 1 times 2 to the power of 8. The 0 that we ignore, and then another 1, plus 1 times 2 to the power of 6. Plus we have a couple of zeros here that we need to ignore, and then another 1, 1 times 2 to the power of 1. And the last 0 that we ignore. So we have 2 to the power of 10, plus 2 to the power of 9, plus 2 to the power of 8, plus 2 to the power of 6, plus 2 to the power of 1. 2 to the power of 10 is 1024. 2 to the power of 9 is 512. 2 to the power of 8 is 256. 2 to the power of 6 is 64. And 2 to the power of 1 is 2. That equals to 1858. As we learned in the previous lesson, an IPv4 address in binary notation looks like this, and if we want to convert it from binary to dotted decimal notation, we need to convert all 4 bytes individually. So let's go on and separate them. It's still the same method as before, so first we write the exponent. We have a 1, we write 1 times 2 to the power of 7. Plus, we ignore all the zeros, and we get another 1, 1 times 2 to the power of 0. 2 to the power of 7 is 128, plus 2 to the power of 0 is 1, and that's 129. Let's move on to the next byte. Same procedure. We have all the zeros that we should ignore. Then we have a 1, 1 times 2 to the power of 3, plus another 0, then another 1, 1 times 2 to the power of 1, plus another 1, 1 times 2 to the power of 0. 2 to the power of 3 equals to 8, 2 to the power of 1 equals to 2, and 2 to the power of 0 equals to 1. The result is 11. Then we have the same number as before, so we're just gonna copy the result. And the last one is a bit more complicated because we have a lot of ones, but still it's gonna be the same procedure. 1 times 2 to the power of 7 plus 1 times 2 to the power of 6 plus 1 times 2 to the power of 5 plus the 0 we ignore, 1 times 2 to the power of 3 plus 1 times 2 to the power of 2, 1 times 2 to the power of 1, 1 times 2 to the power of 0, two to the power of 7 is 128, 2 to the power of 6 is 64, 2 to the power of 5 is 32, 2 to the power of 3 is 8, 2 to the power of 2 is 4, 2 to the power of 1 is 2, and 2 to the power of 0 is 1, and that equals to 239. All we have to do now is separate these results with dots, and we will get the IP address in dotted decimal notation. So let's go and do that. 129.11.11.239. Let me remind you what the IP address looked in binary notation. You can see how much easier it is to read in this notation than in this one. So basically this was the whole process of converting an IPv4 address from binary to dotted decimal notation. And after this lesson you should be able to do it yourself, but you won't remember this unless you try it a few times. So because of that I prepared you a bit of homework for the next lesson. You need to convert this IP address from binary to dotted decimal notation, and I will give you the result and show you how to do it at the beginning of the next lesson. Welcome back, ladies and gentlemen. In today's lesson we are going to learn about IPv4 classes, or so-called classful addressing. But before that we have something else to take care of, and that's the homework from last time. You had an IP address in binary format, particularly this one, and you had to convert it to the dotted decimal notation. I will show you how to solve this question quickly so you can check your answers. First we need to convert this number. We have 2 to the power of 7 plus 2 to the power of 6 plus 2 to the power of 0. That's 128 plus 64 plus 1. And that equals to 193. I will just leave the result here because it's cleaner and less confusing. In the next byte, we have 2 to the power of 7 plus 2 to the power of 1 plus 2 to the power of 0. That's 128 plus 2 plus 1. And this equals to 131. Again, I will delete the calculations and leave only the result here. Moving on to the next byte. We have 2 to the power of 4 plus 2 to the power of 3 plus 2 to the power of 1 plus 2 to the power of 0. This equals to 27. And if you followed all the lessons until now, you should know that this is the highest possible number that you can write using 8 bits, and that number is 255. At the beginning of IP address development, addresses were divided into 5 different groups. We will discuss this architecture even if it's not widely used anymore, because I think that everyone interested in IP addressing should know this. As I said before, in classful addressing, the whole address space is divided into 5 different classes. Those classes are A, B, C, D, and E. If you are wondering how to tell in which class an IP address belongs, it depends on the notation it's written in. If you have an IP address in binary notation, the first few bits can tell you what class it belongs to. However, if the address is written in dotted decimal notation, we need to look at the whole first byte. So for binary notation, if an address starts with 0, it belongs to class A. If it starts with 10, it belongs to class B. IP addresses in class C start with 110. IP addresses in class D start with 1110, and IP addresses in class E start with 1111. On the other hand, in the dotted decimal notation, an IP address belongs to class A if the first number is 0 to 127. It belongs to class B if the first number is 128 up to 191. An IP address in class C starts with 192 up to 223. A class D IP address starts with 224 up to 239. An IP address belongs to class E if it starts with 240 up to 255. In order for you to better understand this concept, I will give you a few IP addresses both in binary and dotted decimal notation. You need to find the class of each of these IP addresses for homework. So take a piece of paper and write down what you think. I'll give you the correct answers at the beginning of the next lesson. Good day everyone! Before we start with this lesson, let's quickly go over the homework from the last lesson. We had these 4 IP addresses and we needed to find out which classes they belong to. The first IP address starts with a 0, that means it belongs into class A. The second IP address is also in binary notation and it starts with 110, and that means it belongs into class C. The third IP address is in dotted decimal notation, and that means we take a look at the whole first number. The number is 14, which puts it into class A. And finally, the last IP address starts with 252, which means that it belongs into class E. I hope that everything is clear until now, but if you have any additional questions, feel free to contact me or ask anything in the Q&A section of the course. Let's continue with learning. In this lesson, we are going to further discuss classful addressing, learn how it works and see the mistakes in this design. Until now, we have learned that there are 5 different IP classes. Each class has a predetermined number of blocks, and each block contains a fixed number of IP addresses. The fact that these numbers are fixed is a big problem about classful addressing. In the past, every company had to request one block in order to get IP addresses for their hosts. For example, if you owned a large company that has 100,000 hosts, a class B block wouldn't be big enough for you, since it has only 65,000 addresses. Therefore, you had to request a class A block, but the problem with this is that millions of addresses would be left unused and wasted. This resulted in only a small percentage of addresses in class A being actually utilized. Medium-sized organizations had to take blocks from class B, but we have the same problem again. An organization with 5,000 hosts has to take 65,000 addresses, and a lot of them go to waste again. Class C was designed for very small companies, as you can tell, which have less than 256 hosts. This block size was too small for many companies, and even if it wasn't, the companies would eventually grow bigger and would need more addresses. Classes D and D are special classes. IP addresses from class D were used for multicasting. Multicasting means to represent several hosts with one IP address. However, they dedicated 268 million addresses for this, which was way too many, but in reality most of them were also wasted. Class E addresses were reserved for future use, but this architecture never really got to that point, resulting in another waste. So let's recap. The thing that you could hear me saying the most during this lesson was waste, 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 and then again more waste. The reason behind that is that classful addressing is really inefficient. The people that designed this architecture had wrong predictions about basically everything that they predicted. Because of this, classful addressing is not widely used anymore. It is replaced by classless addressing, and we will talk about classless addressing a bit more later on. Welcome back everyone. In today's lesson we will learn about network and host portions of an IP address. The network portion is often called net ID and the host portion is also called host ID. The difference between IPv4 classes is not only how they are distributed, there are also some technical distinctions. Network and host portions are one of the differences. The best way to explain these portions is to take one IP address from each class, for example. When I say from each class, I really mean only classes A, B and C because D and D are special classes and the following rules do not apply to them. Here we have one IP address from class A, one from class B and one from class C. In class A, the first byte represents the network portion and the other 3 bytes represent the host portion. This part identifies the network to which the host is attached, and this part identifies one host in that specific network. To better understand this, let's take an example from real life. We can imagine our network like we have one regular street. The street name would be equal to the net ID, but if we want to build a house in this street, however, it would need its own unique house number. The house number is an analogy to our host ID. When we put the street name and house number together, we will get specific information about where the house is located. Network and host portions have the same function. For example, if we want to send a message to our friend, we will say, okay, network layer, take this message and bring it to our friend's computer. It is located in this network, and in case the network has more computers attached to it, I will specify this number as the location of our friend's computer, so you know exactly where to deliver the message. The difference in other classes is only the ratio between the network and host portions. In class B we have 2 bytes that identify the network and also 2 bytes that identify the host. In class C, however, the net ID portion consists of 3 bytes and the host ID portion is represented by only 1 byte. Please keep in mind that these rules do not apply to classes D and D. When talking about these portions in classful addressing, there's also one more thing that I like to mention, and that is the default mask. The mask is also a 32-bit number and it has a specific value for each class. As we can see, when given a masked value, we can determine which class the IP address with that mask belongs to. We can also determine the net ID and host ID of said IP address. The ones represent the number of the network portion bits and the zeros represent the number of the host portion bits. The default mask values in classful addressing are predetermined and fixed, however that will change with classless addressing. And before I forget, I'll say it again, these rules do not apply to classes D and D. Greetings ladies and gentlemen, with this lesson we will be introducing something new, classless addressing. As we already learned, classful addressing was very inefficient in distributing IP addresses, which resulted in the development of this new architecture called classless addressing. From the name of this architecture we can conclude that we don't have any different classes, however the IP addresses are still requested and granted in blocks. Since we don't have classes anymore, the network and host portions aren't fixed, so they can have different values depending on our needs. For example, we can have this IP address and say that the net ID consists of 11 bits and the host ID consists of 21 bits. Or maybe we want the net ID to be 20 bits, which leaves only 12 bits for the host ID portion. You get the idea. Well, obviously, the network portion can have many different values in classless addressing, so we also need a nice and simple way to denote this value. Therefore, we will introduce a new notation called classless interdomain routing notation, or CIDR in short. Sounds complicated, but it isn't. This is just another way of writing IP addresses, like when we had binary and dotted decimal notation before. Here's one example of the CIDR notation. So whenever we see a slash after an IP address, we know that it's in this notation. The number after the slash indicates the number of net ID bits. In this case we have 22 bits for the network portion. Obviously, the higher this number is, the lower the host ID portion is. And if we decrease the host ID portion, the less computers can be attached to the network. It's a bit weird to work with CIDR while the IP address is in decimal notation, So whenever you need to do some calculations, first convert it to binary. Until now we have only learned how to convert numbers from binary to decimal, but I'll show you how to do the reverse conversion in the next lesson, and by the way, it's much easier than binary to decimal. For example, when given this IP address, we are able to determine how many computers can be connected to this network, and that by just knowing this single IP address. So as I said, we need to do some calculations, and therefore we will take the one in binary notation. If we want to calculate the maximum number of computers that can be attached to this network, first we need to convert all the network portion bits to zeros, because we are focusing on hosts and the network is not important for now. After that we convert all the host ID bits to ones. Then we convert this number to decimal. It's going to be 1023. In theory, this is the maximum number of computers that can be in this network. However, in reality, the first and last addresses are reserved for something called network IP and broadcast IP. We will learn about that in a while. This means that we can have 1023 minus 2, which is 1021 computers in this network. When given a single IP address from one network, we are also able to determine the addresses of the first and last hosts in that network. To find the address of the first host, let's take a look at the original address. This time we don't touch the net ID portion at all, but in the host ID portion we convert the rightmost bit to 1 and the rest to zeros. This is the address of the first host in this network. In order to find the last host, in the host ID portion, this time we convert the rightmost bit to 0 and the rest to 1s. This is the address of the last host. Now let's talk a bit more about those two IP addresses that are reserved, the network IP address and the broadcast IP address. The network IP is basically the address of just the network without any computers or routers attached to it. This address is pretty much useless for a regular person. To calculate this address, however, you take the original address that you got and simply convert all the host portion bits to zeros. In our example, that's the IP address that we got in the first place, so we don't need to convert anything. The broadcast address is a bit more useful. The purpose of this address is to send something to every computer in that network. For example, if you want to send a message to everyone, you could go ahead and send it individually to all the 1021 computers. But if you want to do it faster and more efficiently, you can simply send it all at once using the broadcast IP address. In order to calculate this address, you simply convert all the host portion bits to ones. That's it for now. See you in the next lesson with decimal to binary conversion. Welcome back everyone. In this lesson we will learn how to convert numbers from decimal to binary numeral system. Just as before, the simplest way of doing this conversion is just googling decimal to binary converter. So I'll go on and show you that really quick. You enter the decimal number here, click on convert, and it will give you that number in binary format. If you want to be able to do this without Google, stay tuned. If you ever wondered why humans use the decimal numeral system, it's because most humans have 10 fingers. Therefore, throughout history, this numeral system appealed to us as being the simplest. However, there are still some communities in the world that use different numeral systems, but of course, they are the minority. Let's get to the point. For example, we want to convert this simple number from decimal to binary. The first step is to divide the number by 2. 10 divided by 2 equals to 5. 5 times 2 is 10, which means we got a remainder of 0. The next step is to divide this result by 2, and we will keep dividing the results by 2 until the result equals to 0. 5 divided by 2 equals to 2, and the remainder is 1 because 2 times 2 is 4. Let's divide the result again. 2 divided by 2 equals to 1 and the remainder is 0. We need to divide the result again. 1 divided by 2 equals to 0 and the remainder is 1. Since the result is 0, we don't need to divide anymore. If we read the remainders from bottom to top, we will get our number in binary format. So 10 in decimal format equals to 1010 in binary format. It doesn't matter how many zeros are in front of this number, it won't change the value. So we can go ahead and write 4 zeros 1010 because we are mostly using 8 bits at a time in IP addressing. However, if we added some zeros after this number, it would change the value. So adding zeros before is okay and adding zeros after the number is not okay. One common mistake the people make in this conversion is reading the remainders from top to bottom. Let's do one more example with a bigger number this time. 237 divided by 2 is 118 and we get a remainder of 1. 118 divided by 2 equals to 59 and the remainder is 0. 59 divided by 2 is 29 and the remainder is 1. 29 divided by 2 is 14 and the remainder is 1 again. 14 divided by 2 is 7 and the remainder is 0. 7 divided by 2 is 3 and the remainder is 1. 3 divided by 2 is 1 and the remainder is 1. 1 divided by 2 equals to 0 and the remainder is 1. Since we have a 0 here, we don't divide anymore. Let's read the result from bottom to top. We get 11101101. And this is the number 237 in binary notation. Honestly, this is as complicated as it gets. And to make sure everybody gets the hang of this, try converting these three numbers from decimal to binary for homework. 38, 111 and 255. As always, I will give you the results in the next lesson with a quick explanation in case anybody is confused. Welcome back, ladies and gentlemen. As promised, first we will go over the homework from the last time with a brief explanation. We had three numbers that needed to be converted from the decimal to binary numeral system. The first number was 38. The first step is to divide it by 2. 38 divided by 2 equals to 19 with a remainder of 0. 19 divided by 2 equals to 9 with a remainder of 1. 9 divided by 2 equals to 4 with a remainder of 1 again. 4 divided by 2 equals to 2 and the remainder is 0. 2 divided by 2 equals to 1 and the remainder is 0 again. And finally 1 divided by 2 equals to 0 with a remainder of 1. We have a 0 here, that means we're finished. Now we read the remainders from bottom to top. So the result is 100110. And this is the number 38 in binary notation. The next number was 111. First step is to divide it by 2 as always, which is 55, with a remainder of 1. 55 divided by 2 equals to 27, with a remainder of 1. 27 divided by 2 equals to 13, and the remainder is 1. 13 divided by 2 equals to 6, and the remainder is 1 again. 6 divided by 2 equals to 3, and the remainder is 0 this time. 3 divided by 2 equals to 1 with a remainder of 1. And finally 1 divided by 2 equals to 0 with a remainder of 1. As we have a 0 here, that means we're finished. Now we read the remainders from bottom to top again. So the result is 11011111. This is the number 111 in binary notation. And finally the last number is 255. And we already learned that this is the highest number that we can write using 8 bits and therefore we can convert it by heart, which is 8 ones. There you go. So that's it for the homework, and let's move on to the next lesson. In this lesson we will talk a bit more about classless addressing. We have already talked about requesting a block of IP addresses even in classful addressing, but how do you actually do it? How do you request and get a block of IP addresses for yourself? You must be thinking that this is nonsense because you are using the internet normally without going through with this hassle. In fact, your internet service provider, or ISP, has already completed this for you. They are the ones that do this beforehand, and then they give one or a few IP addresses to their customers, depending on where you live or how much you pay for internet access. This means that if you don't own a huge company, or if you don't want to start your own ISP company, chances are that you will never need to worry about requesting IP addresses in blocks. Starting an ISP company can be extremely challenging, and trust me, when I say extreme, I really mean extreme. However, maybe some of you want to try their luck with this, because there can never be enough competition in the ISP world. Or maybe some of you are just curious like myself. In that case, the authority in charge of allocating IP addresses is called the ICANN, which stands for Internet Corporation for Assigned Names and Numbers. This is a corporation that operates internationally. Bottom line, this is the big boss of IP address allocation. Usually only ISPs request blocks from this company, and those blocks are huge, but later they are split and divided into smaller sub-blocks and distributed to the ISP's customers. It is also possible to request multiple blocks of addresses. However, to keep things simple, the ICANN has made some restrictions in that case. The first restriction is that the requested blocks must be one after another. So that means you can request 2, 3, 5 or even more blocks, but they have to be in a row. The second restriction says that the number of addresses in one block must be a power of 2. So you can request a block that has 2, 4, 8, 16 and so on addresses in it. And the last restriction says the first address must be evenly divisible by the number of addresses. I do not know why they specifically insist on these restrictions, but I assume that it's just to keep things organized for themselves. As I said, they are the big boss and they can make rules as they like. Welcome back once again. The time has come to learn about IPv6. The best way to explain it is probably to compare it to IPv4. The first question that comes in mind is, why does IPv6 exist? We have learned before that IPv4 addresses are running out because the numbers of networking devices are becoming overwhelming. The purpose of IPv6 is to eliminate that problem with introducing a bigger number of addresses. That number is 2 to the power of 128, and we have also learned that before, but let's get into the details now. When you look at it like this, you might think, sure, it's bigger than 2 to the power of 32, but it's not that much bigger, right? Wrong. Let's find out how big this number really is. There's this website that I like to use for calculating stuff or finding mathematical explanations called Wolfram Alpha. Many of you have probably heard about this website before, especially college students. Let's enter our number here, 2 to the power of 128. So here is the real number. We can see that it has 39 digits, which is absolutely ridiculous. But if you still don't realize how big the number is, let me give you one real-life comparison. We can assign an IPv6 address to every single atom on the surface of Earth. That seems like a lot of addresses, right? Well, I still wasn't done. We can do this more than 100 times. That's how big this number really is. Surely, with so many addresses, we need a different way to represent them. Here are a few examples of IPv6 addresses. We can see that they consist of 8 groups and each group has 4 hexadecimal digits. If you look carefully at the other addresses, you might notice that we only have 2 digits in this group. That's because we can eliminate leading zeros and it will still remain the same address. Also in the last one you might notice that one group is completely missing. That's because all digits in this group were zeros and we can also eliminate them. When it comes to the usage of IPv6 addresses as of today, IPv4 is still used a lot more. But IPv6 is certainly expanding quickly. I found this interesting graph by Google while doing my research, and it shows us that IPv6 wasn't used a lot a few years ago, but in the late years we have a rapid expansion. Approximately 16.5% of web traffic is using IPv6 at the time of making this video, and that is the 28th of March 2017. As we can conclude, IPv4 and IPv6 are kinda coexisting right now, and we are probably going to be in that spot for a few more years until IPv4 is completely replaced. One more fun fact is that IPv5 exists also, but it never really made its way to the public use. If you want to know more about this, you can do a little research. It's mainly known as Internet Stream Protocol version 2. So we have IPv4, which was developed in 1983. We have IPv5, which was developed in 1987, and we have IPv6, which was developed in 1999. An interesting question that comes to mind is, will there ever be a need for IPv7? This is just my personal opinion, but I was shocked that so many people think that we'll never run out of IPv6 addresses. I understand that the number of addresses seems tremendous, but so did 4 billion IPv4 addresses back in 1983, and look what we have now. Of course, people at that time couldn't understand how the world is going to change. We can't understand what will happen in the future either, but we certainly can learn from the past mistakes. I'm looking forward to the day of a new technical revolution when IPv6 addresses will be running out. Please note that this was just my personal opinion, and I'm not asking you to agree with me in any way. Welcome back, ladies and gentlemen. To continue with this course, let's introduce one new concept first. We will break it down into key points, and then I will explain all of these important parts separately and in detail. Let's see how a computer from a home network is accessing a website on the internet. For example, let's say you have cable internet, which means the coaxial cable is connected to the router. The router can have multiple Ethernet ports so you can connect your devices directly. If the number of ports is not enough for you, then you would need to buy an additional switch to connect all of your devices. However, let's say that for this example the router does have enough ports and that we have 3 computers connected to it, which forms our very own LAN or local area network. Each computer has a MAC address and an IP address. Computers are only communicating with each other, which means the communication doesn't go past the router or switch. Their IP addresses do not need to be globally unique. They have to be unique in this network obviously, but my neighbor can have a LAN network using the same IP addresses. These addresses are called private IP addresses. Since my computers and my neighbor's computers can't communicate with each other unless we are using the internet, it doesn't matter that we are using the same addresses. In fact, this is a method to reduce IPv4 waste. To better understand this, you can imagine the network as a building and the computers would be apartments. Each apartment has a unique number in this building, but nothing prevents another building to have the same apartment numbers. Back in our example, let's say one of the computers wants to reach out to a destination outside of this LAN to access a website. In order to access a website, you open your browser, type in the website address and press enter. When you press enter, the website address is translated to an IP address using DNS, and you are actually sending a request to the server with that IP address and asking for the HTML code. The request goes to your router, and since it's going outside of the LAN network, we might have a big problem. Maybe more computers have the same private IP address as you, and the website server wouldn't know where to send the requested code. Therefore, you will be assigned a public IP address, which is unique even outside of the LAN, before the request leaves. The request then travels to your ISP and then out to the internet where the website server is located. Website servers have static IP addresses, but personal computers usually have dynamic IP addresses. The server gets your request and replies to you with the code, which is then used by your browser to show you the content of the website. All of this might appear to be really complicated for beginners, so we will split it into these parts: private IP addresses, public IP addresses, DNS, static and dynamic IP addresses. I will explain all of these topics in the next few lessons, and I also want to encourage you to ask any questions you might have in the Q&A section of the course. Welcome back once again. This lecture will be about private and public IP addresses. we will learn about the difference between them and how they are used. Many of you probably already understood the difference between those addresses in the last lecture, but in case you didn't, public IP addresses are used to identify a device on the internet. These addresses are unique, meaning that nobody on the internet has the same public IP address as you at the same time. On the other hand, we have private IP addresses, which are used for private networks, mostly in home local area networks. Devices with this type of addresses cannot access the internet, because private IP addresses are not globally unique. That being said, we can conclude that private and public IP addresses have a totally different purpose. Therefore, you will need to know how to tell which IP address is private and which one is public. When it comes to private IP addresses, the Internet Engineering Task Force and the Internet Assigned Numbers Authority reserved the following IPv4 addresses for the use in private networks. We have the Class A private IP addresses, which start with 10.0.0.0 up to 10.255.255.255. These addresses are easy to recognize because whenever you see an address starting with a 10, you immediately know that's a private IP address. We have the Class B private IP addresses that range from 172.16.0.0 up to 172.31.255.255. And finally, we have the Class C private IP addresses that start with 192.168.0.0 up to 192.168.255.255. Those are also easy to recognize because whenever you see that an address starts with 192.168, you immediately know that it's a private IP address. Maybe you're thinking that it's not so important to learn all of these ranges by heart and to remember them, and I totally agree with that because you can always look them up when you need them. However, if you are taking a networking exam such as the CCNA or a simple exam in school or in college, I will strongly suggest to remember these ranges, because you might face a question like this. Which of the following IP addresses are routable on the internet? We already know that private IP addresses are not routable on the internet, and therefore the best way to answer this question correctly is to first eliminate private IP addresses. And that's why you need to learn these private IP address ranges by heart, because you won't have access to books during your exams. There are a few more IP addresses that are not routable on the internet besides private IP addresses. These addresses are mainly reserved for something else. The best examples of such addresses are the loopback or localhost address is 127.0.0.1. Another example is the APIPA address or the automatic private IP addressing. This IP address range is 169.254.0.1 up to 169.254.255.254. Private network administrators can randomly assign these addresses, however problems might occur when we want to connect two or more private networks together, because the address space is small and some devices might have duplicate IP addresses. To solve this issue, the network administrator would need to manually change the address of each device or use a network address translator gateway between the two private networks. It will automatically find the duplicate IP addresses and masquerade them so that everything works fine. If you want to see your computer's private IP address, go to your Start menu, type in Run, click on the application, type in CMD and press OK. This will open up a command prompt window where you can type in ipconfig -all and press enter. This will give you some information about your network adapters. For example, here is your physical or MAC address and here is your private IP address. To find your public IP address, however, you can simply go to Google and type in "What's my IP?" Let's just open up the first link that comes up, and it will tell me that this is my public IP address. This is the address that I'm using to connect to the internet. That's it for now, and for the next lesson I plan to do a hands-on project where I will show you how to create your very own private network from scratch. Welcome back, ladies and gentlemen. This lesson will be a bit different. I want to teach you how to create your own private network in order to make this course more interesting and so you can get a better understanding of networks. This will be a simple hands-on project where we will create a small private network with 3 devices connected to it. The network will look something like this. I will use a wireless router which has 4 Ethernet ports. Then I'll connect my desktop PC to it using an Ethernet cable and use my PC to access the router settings. After everything is set, I'll also connect my laptop using another Ethernet cable, and finally I'll connect my phone using the Wi-Fi just to show that everything is functional and works fine. Let's get through the parts list quickly. This is my old wireless router. It was made by a company called TP-Link and I don't use it anymore. At the back we have the wireless antenna, along with a power slot and 4 Ethernet ports. The blue port is where you would connect a modem if you wanted to give internet access to this private network. However, most ISPs today have devices called all-in-one modems or all-in-one routers, and that's why I don't use this router anymore in particular. However, there are some people that still prefer to have separate devices for their modems and routers, such as this one. Our network will not have access to the internet, so the blue port will be left unused. We will connect our devices to ports 1 and 2 using Ethernet cable, and the third device will be connected wirelessly. If we wanted to connect more than 4 devices to this network via Ethernet cable, we would need to use an additional switch. In addition to this, we will also need 2 Ethernet cables, which I have right here, and of course a power cable for the router itself. So basically this is everything that you need to create your very own private network. So let's start with building this network. Since the router is the main point of the network, let's start with that. Well, obviously for the router to work, you have to first plug in the power cord, which I can do right here. Now plug it at the back of the router. And we can see that it's working properly since we have the power and the system lights blinking. And we also see that the wireless is working since that light is also blinking. But now we have a router that doesn't do anything because there's no devices connected to it. At least that's easy to fix. First I want to connect my PC so that I can access the settings of the router before I connect any other device. I already plugged the Ethernet cable in the Ethernet port of my PC because it's hard to get there, and now we have to plug it to the first port of the Ethernet. We can see that the first port is lighting up, which means it's working properly. Now in order to access the settings of this router, you have a specific IP address written at the bottom of it usually. That address is 192.168.1.1. It will require you to enter a username and password, which is also written here. If you can see, it's admin and the password is also admin. So let's go on and do that and see what we get in the settings screen. To get to the settings screen of the router, open up your web browser of choice and type in the IP address from the bottom of the router. It was 192.168.1.1 and press enter. Authentication is required. The username was admin and the password was the same. Press on login and it will take us right to the settings screen. At the left side of the screen you have some categories, for example basic settings and advanced settings, but let's get into that later. In the middle of the screen you have basic information about your network or connection or router. You might notice that it's written in red that WAN is disconnected. That means that using this network we don't have access to the internet because obviously we didn't plug in the modem cable. At the right side of the screen you have some basic help explaining all of these parameters and everything that you need to know about them. Please note that this settings screen might be different depending on what router you're using, but it doesn't matter in the long run because if you master to use this settings screen, you will also know how to use it on different routers because it's mainly the same concept. Let's go on and click on Quick Setup for now. The Quick Setup will tell you how to configure your basic network parameters. Press on Next. We didn't talk yet about dynamic IP or static IP addresses, but we'll do so in the following lessons. But for now, let's just choose dynamic IP as our WAN connection type and click on next. This is whether we want our wireless signal to be enabled or disabled. Obviously, we want it to stay enabled because we want to connect our smartphone later on. The SSID is the name of the wireless network. Let's set it to Udemy lesson, for example. The region is where you choose where you're from. For some reason it doesn't let me choose my country, but it should work fine like this. Leave the channel at automatic, and for the mode I have only two settings here with my router, and I will choose the 802.11g. Press on next. That's it for now, and the router should be ready and set for use. When you click finish, it should restart and reload the page. Once the page has reloaded, for security reasons you obviously want to put up a password for your wireless network so that you don't have any intruders. In order to do that, go to your wireless settings, and at the middle you should see a little box saying enable wireless security. Select that, and for security type you should select VPA2-PSK. Leave the security option and encryption at automatic, and here's where you type in your actual password. It should be between 8 and 63 characters long. So let's type in something cool like Udemy123. Click on save, and the config was uploaded again, which means the settings were successful. Now that we have the settings out of the way, we are ready to connect more devices. In fact, now I will be connecting my laptop. I will take the second cable and plug it into the Ethernet port of my laptop. I will plug the other end into the second Ethernet port of the router, and I'll check if the second light is blinking. We can see that it's blinking, and that means that the router has recognized the laptop as a network device and that the connection is ready so that devices can communicate using this router. Now let's go on and connect the smartphone using Wi-Fi to see if that works. I'll go to my wireless settings. Here's the Wi-Fi, Udemy lesson, and if I remember correctly, the password was Udemy123. Press on connect, and the connection was successful. So now we have these three devices connected to this router, which forms our very own private network. Now we'll do some ping testing in order to make sure that everything is working correctly and that devices can communicate with each other. As I said, now we'll be doing ping testing in order to tell if all the devices are connected properly. To ping somebody actually means to send small packets of data to them and request a response. This process is repeated a few times, and then we are measuring the average time of completion and the latency. If the process is completed fast enough, that means we have a good and stable connection, and if it's not completed at all, that means we either did something wrong with setting up the network or we have the wrong address. In order to do pings, we need to know the private IP addresses of all the devices. So I already got the private IP addresses and written them down on a paper so that we can start. Go to your start menu and type in run, press on the application, type in CMD and press OK. The command prompt window will pop up and we can enter the command for pinging. The command is ping, then we have a space, and then we type in the private IP address of the device that we want to ping. So let's try the laptop first. The IP address of the laptop is 192.168.1.101 and press enter. We can see that we're getting replies from the laptop quick, and we have the statistics here. We can see that no packet was lost and that we have a small or non-latency. That means we have a very good connection with the laptop. Now let's try with the smartphone because it's connected wirelessly and we need to test that also. Ping. The IP address of the smartphone is 192.168.1.102. Press enter, and we are also getting the replies from the smartphone, which is good. No packet was lost and we have a small latency. It's bigger than from the laptop, but it's still acceptable and very good, and the connection is good. Now if we were to ping test some device that doesn't exist, or let's say hypothetically it was connected wrongly or the cable is bad, for example ping 192.168.1.105, we'll get something like this. Some weird responses like request timed out, packets were lost, and stuff like that. This means that there's some problems. Well, I mean in our case the device doesn't exist, so this is perfectly normal. All packets were lost and we can tell that there's something wrong with this device if there was any. So that's everything that you need to know about setting up your private network and how to use these private IP addresses. See you in the next lesson. Welcome back, ladies and gentlemen. In this lesson we will learn about static and dynamic IP addresses, along with a bit about DNS or domain name system. I would like to start off with dynamic IP addresses because I assume most of you are using one. Internet service providers usually give these addresses to most of their regular customers. When something is dynamic, that means that it's in a state of constant change, and that's exactly the perfect name for these addresses. For example, if you are using a dynamic IP address, you will only have it for a small time period and then it will change to a new address. These addresses will always change after the predetermined time period has expired. The device that assigns you new dynamic IP addresses is called a DHCP server, and this is not the only thing it does, but it's very important. Moving on, next we have static IP addresses. As you might have guessed by now, these IP addresses never change automatically, meaning that a device with a static IP address will always have that same address unless we change it manually. These type of addresses certainly have their strengths and weaknesses. However, the main difference between static and dynamic IP addresses is who uses them. While dynamic ones are used by the average web surfing human, static addresses are mainly used for websites, and now we'll see why. A website is a remote location on the internet, and in order to access that location, you need the website's URL or IP address. When you type in the URL in your browser and press enter, it's translated into an IP address using DNS or domain name system. The only reason why we use an URL is because it's easier to remember than the IP address. The best real-life analogy to a DNS is a phone book, but instead of people's names and phone numbers, it holds URLs and IP addresses. That's also the reason why websites use static IP addresses. If they used dynamic ones, it would just make this process more complicated because the DNS phone book would need to be updated every time the address changes. That being said, we can conclude that we do not need to know the URL in order to access a website. We can just use the IP address instead. If you don't trust me, I'll demonstrate this for you real quick. Let's try it with facebook.com. If some of you don't know this already, this is the website's URL address and this is one way of accessing the website. However, we said that we can access the same website using its static IP address. But how are we supposed to find that IP address? Well, the simplest way that comes to my mind is to just ping this website and the IP address should be visible. So let's go on and try that. Open up your command prompt window like we did in the last lesson and type in ping facebook.com. And here we have Facebook's static IP address showing. You can do this method to find any IP address of any website that you like. Let's try to type this into our browser. 31.13.84.36. Press enter and we can see that we are redirected to the same page again. This type of accessing a website is called direct IP accessing. However, some websites might prevent you from doing this for security reasons. For example, let's try to do this with udemy.com. Ping udemy.com and we can see its static IP address. So let's try to access it directly. 104.20.65.82. Press enter and we can see that we have a problem here. Direct IP access not allowed, and this is what I was telling you about. With this lesson we are concluding the IP addressing course. I want to thank you for your time and attention, and if you have any additional questions or feel like I didn't explain something properly, please contact me or ask questions in the Q&A section of the course. I also want to encourage you to leave reviews saying what you liked or didn't like about this course so I can improve my work in the future. Thank you again.